In this paper, we present FinderNet, a data augmentation, free canonicalization aided loop detection and closure technique for point clouds and 6 DOF separation. Loop detection and closure is a critical part of any SLAM system, where given a set of poses and constraints, we aim to optimize the robot's pose graph such that the accumulated map has no errors and our map is coherent and obeys all of our poses and constraints. Our method FinderNet is 6 degrees of freedom view invariant, requires no large data augmentation during training, has both loop detection and loop closure capabilities, and is data efficient through learnt embeddings. We observe that point clouds are inherently unstructured, leading to inaccurate loop detection and closure. By leveraging the benefits of canonicalization, we represent the point clouds as a digital elevation map, similar to something you would see in a topographical map. This exposes the rich spatial structure of the environment. The video on the left is a sequence from the Kitty dataset, and the video on the right is the respective DEMs for each point cloud scanned. We observe that DEMs are a much more compressed version of data to use as opposed to the actual point clouds itself. Our architecture is split into 4 parts: DEM generation, the autoencoder and DEM reconstruction, the loop detection module, and the loop closure module. Beginning with DEM generation, we first assume that all urban environments or all environments a robot is reasonably expected to run in have a dominant plane that we can use as our canonical plane. We first extract this plane using ransack from both positive and anchor DEMs and then rotate our point cloud in our top view discretization process such that our view is perpendicular to this canonical plane. We do so by first performing a coarse roll and pitch canonicalization by trying to align the canonical plane with the z-axis and then performing ICP with this coarse canonicalization result as our initialization. Afterwards, we convert the point cloud into a DEM by discretizing over the entire point cloud and flattening a 3-dimensional structure into a 2-dimensional DEM. We then have an autoencoder and a DEM reconstruction module which aims to train encoders to generate flexible embeddings that are then sent into a differentiable yaw transformer, one of the novelties of our paper. The differentiable yaw transformer is a module that performs a series of operations to help us estimate the most accurate yaw in between 2 given DEMs. Given an anchor and a positive or negative DEM, we first convert both of them from a Cartesian form into a polar form. We flip and pad the positive or negative DEM, and then we run a cross correlation using the anchor as a kernel over the flipped and padded positive or negative. By softmaxing and extracting the best angle and the weighted sum of angles, we obtain the most likely relative yaw. This module is entirely differentiable and is what lets our entire architecture be end-to-end trainable. Moving on to the difference layer, both positive and negative embeddings are then fed through a series of conv nets before being fed into this actual module. A simple example of what we're doing is unsqueezing each height and width channel and converting a 2D DEM into a one-dimensional line with n channels, and then tiling this across both dimensions. So the positive or negative DEM is tiled across the x-axis and the anchor DEM is tiled across the y-axis. Exact mathematical representations of the previous operations can be found within our paper. We then perform loop closure using standard procedures and the transforms obtained from before. We can use the difference in between both canonicalized planes, which we store, and our generated yaw to actually perform loop closure. Our difference module actually lets us determine whether 2 given loops are true loops or a false positive. We train our model through triplet loss, where anchor positive pairs are 2 DEMs or 2 point clouds that are separated by a maximum of 4 meters, and anchor and negative pairs are separated by 4 to 10 meters. This scheme allows us to have semi-hard examples for our negatives letting our model be much more flexible and confident and transferable on other data sets as well. We transfer 50 by 50 point clouds into DMs of 500 by 500 pixels. Loop detection is evaluated through our average precision, and loop closure is evaluated on the average translation error and rotation error. We use the RMSE to evaluate the state estimation error, and memory is measured in kilobytes. For a full set of results in our paper, you can look at the appendix and the resulting sections. But our method is comparable to SOTA methods such as Lyosam, etc. A qualitative evaluation of our results shows that a loop detection and loop closure, after being converted into DEM format, does indeed align both loop candidates.